Thank you and welcome everybody. I hope you can hear me okay. In the back of the room, the front of the room? Awesome. All right, we'll do our best here. Thanks again for the invitation. Peg asked me to talk about 3 topics today, and I hope I will be able to put all 3 of them into the time allotted. I'm going to talk a little bit about the James Webb Space Telescope that's orbiting 1 million miles from Earth and sending back some fantastic pictures. I'm going to talk a little bit about an adventure that Peggy and I had back in February in Denver, Colorado, and other places related to something called the Lucy mission, which is a spacecraft that's on its way to the asteroid belt right now. And then a quick update on our plans for the International Dark Sky Discovery Center, fundraising, and a short video on that. I'll take questions at the end. I think that would probably be the best. Now, there's going to be a very subtle segue between the James Webb Telescope talk and the Lucy mission talk. So keep your eyes peeled and see if you can spot that as it goes by really fast. All right. So, of course, this thing doesn't want to work anymore. There we go. So, what is this thing called the James Webb Space Telescope? Well, it's a big telescope, and it's out in space, and it's named after James Webb, who was the administrator of NASA during the entire Apollo program that got mankind to the moon 6 times. So, this is a picture of the James Webb Telescope, JWST, compared to the Hubble telescope, which has now celebrated its 30th successful year in space. Been up there, I know, it doesn't seem that long, does it? Got a few things to say about that too. And as far as size goes, you can see that the James Webb Telescope is a teensy bit bigger than the Hubble. And it's also made up of these 18 hexagonal segments, so it was quite a bit more difficult to construct and test. But we did it, and it's working fantastically. What I wanted to talk about today is a little bit of physics. So how many people remember physics in high school? No hands up. All right, we're in trouble. So we got to go really fast here. So the visible light that we see is only a small part of something we call the electromagnetic spectrum, which goes all the way down to X-rays on one end and all the way up to radio waves on the other. So the Hubble is taking pictures in visible light. That's pictures like you could take with your camera of the sky or of your neighbor or your loved one. But as I said, the electromagnetic spectrum goes in both directions. So as the energy of the waves get higher and they get a little shorter in wavelength, you go down to X-rays, which is what we get at the dentist, and gamma rays, which are dangerous radiation. And in the other direction, well, you've got infrared light, and then if we go farther than that, microwaves and all the way up to radio waves. Some of those radio waves, those wavelengths are as much as hundreds of feet across from peak to peak, and that allows them to skip around the Earth. So, you know, radio operators and hams can talk to people on the other side of the planet because those long radio waves can bounce off the atmosphere and work their way around the planet. The advantage that the James Webb has by being sensitive to infrared light is that infrared light can pass through the dust that populates the distant parts of the universe, and that allows us to see things farther away that the light would otherwise be absorbed. So the visible light, we can only see so far, and I'll get to talk about this a little bit later. Beyond a certain distance out into the universe, all the visible light coming from those very, very distant galaxies is absorbed as it tries to work its way through all this dust. And so we see nothing out in the farthest reaches of the universe. But the James Webb Telescope was designed to be sensitive to infrared light. And the scientists who put together the proposal had said, we need a telescope sensitive to infrared light, out in space, of course, so it's easier to see things in the distance without the atmosphere getting in the way. The infrared light will let us see deeper into the clouds of dust that are making up stars in our local area, and also the infrared light that's coming from the very, very distant galaxies that were the first ones to form as the universe formed. So that's why we look in a different part of the wavelength spectrum with the James Webb. This is the mirror for the Hubble telescope. It was ground in Danbury, Connecticut, and I was actually living there at the time and had no idea that it was under construction a mile from my house at Perkin-Elmer, which was a company that was later purchased. And you can see that they were grinding this mirror under very strict controlled conditions to a fantastically careful and accurate shape. When we launched the Hubble into space and took a picture of, well, this is a picture of a galaxy called M100 from Earth. And you can see a few stars in there, but there's a lot of detail that's lost because we have to look through the atmosphere. So we take this 6-foot diameter mirror, we launch it into space at the cost of hundreds of millions of dollars, and we take a picture and we say, this is going to be way better than we can see from Earth. And this is what we got. Oops, what's that? So what went wrong? We have no idea what went wrong. So for 2.5 years, we investigate what went wrong. We take a picture of a star that you can see. This star is a picture from Earth. Let's take a picture of that star with the Hubble telescope and see what it looks like. That's what it looks like in the Hubble in its initial mirror. What happened? The mirror was ground very, very accurately to the wrong prescription. There was a tiny 1 millimeter mistake in a device that was shining laser light down to tell them when to stop grinding glass, and they ground 1 millimeter of glass off the edges of the telescope too much. And that's an enormous error. I mean, in the world of precision optics, 1,000th of a millimeter is a bad error, and this was a full millimeter. So huge, huge problem. So what did we do? We sent astronauts up to repair the telescope by giving it prescription glasses. We pulled one instrument out of the telescope in space during spacewalk and inserted a device that would then send small, tiny corrective mirrors into the path of the light being reflected from the big mirror at the back of the telescope. And this solved the problem just the same way you see better when you put glasses on. We also were able to send 3 more missions up to the Hubble in the first 10 years of its life to replace the solar panels and the failing gyroscopes. There were a lot of problems with it, but since the 4th and last repair mission, everything's been great, and it's been sending back lots of pictures. This is the difference between that M100 photograph before and after the corrective optics were installed. So Hubble's been doing a great job for 30 years, and if the gyroscopes stay working, we could expect another decade or so out of it before it kind of fails at some point. But it's only 332 miles up from Earth. The James Webb Space Telescope orbits 1 million miles from us. And there's no more space shuttle to take astronauts out even 300 miles, much less 1 million, to fix anything out in space. So to avoid any possibility of another incredibly embarrassing disaster like we had with the Hubble mirror, the James Webb Telescope spent an extra 10 years and an extra $7 billion in order to test it on Earth in such a way that we could be 99.99% sure that nothing like that would possibly happen. Here's a picture of the frame that's going to hold those 18 mirror segments in a clean room and at the Jet Propulsion Laboratory. And there are a picture of the 18 mirrors inside some protective shells after they'd been created. Once the mirror was totally assembled and the telescope was totally assembled, it was placed into this giant vacuum chamber where all the air was pumped out, and it was refrigerated down to 400 degrees below zero and then shaken like crazy, as it would be during the launch, in order to make sure that if anything was going to break, it was going to break right here on Earth where we could fix it after it warmed up for about 30 days to get it out of this thing. So there wasn't a lot of time, but that's how you get things to work well when they're 1 million miles away out in space. There's a couple of pictures of it. You can see that it has to be folded up, of course, to fit inside of a rocket, but it unfolds itself like this, and there's a mirror up here, so the light reflects off these 18 mirrors, bounces up to this mirror, comes back down, goes through a hole, and down under here are where all the cameras are that are actually going to give us the images. It's powered by solar panels, and the solar panels are enormous, but they have to be tested here on Earth, and they're not going to support themselves on Earth's gravity. So during the test of unfolding and refolding them, you can see that they're actually supported on a thing that kind of like the shower curtain that you have in your bathroom, to make sure that those hinges don't get stressed too much so that they won't work when they're out in space. So all that stuff has to be planned and executed carefully on Earth. Now let's talk about the mirrors for 1 second. Those 18 mirror segments are very, very special. They had to be carefully carved, and only the center mirror section is actually a perfect parabola on both sides. From there out, all the mirror sections have to be ground to be part of a much larger curve. So each one has a unique shape, a unique curve, a unique dish shape to it as they go out from the center to the edges. And so each one has to be carefully assigned to its place and then carved, tested, maintained. So here's a little video on the process of how those mirrors were made.
But before James Webb was even assembled, the telescope's mirror also had to go through a crazy journey. The 18 giant hexagonal segments that form Webb's mirror are made from a metal called beryllium. This metal was chosen to keep the overall mass of the mirror extremely low, while still retaining lots of strength. Despite being about 3 times larger than Hubble's mirror, Webb's mirror only had a fraction of the mass. But in order to construct these perfectly polished mirror segments, they had to make 14 stops at 11 locations all across the U.S. The first journey started in the mountains of Utah, where the beryllium powder was mined and shipped to Ohio, where it was purified and turned into individual mirror blanks. Then the blanks were sent to Alabama, where each one was machined into a honeycomb structure to reduce mass. The next destination was California, where the mirrors were polished to the exact shape, perhaps the most crucial part of the process. After this, the segments made several trips across the country, undergoing years of testing to check that they were polished correctly. On the 9th journey, the mirror segments traveled to New Jersey, where gold was evaporated over them inside of a vacuum chamber to form a very thin coating. After some more testing, the mirror segments ended up in Maryland, where they were assembled together and attached to the main instrument model.
Now, the amount of gold that it took to coat that entire mirror was approximately the amount in 1 Krugerrand, about an ounce of gold. The layer of gold on there is only about 9 atoms thick. And that's enough because gold turns out to be a very good reflector of infrared light. And so that's why gold was chosen to be the coating of those mirrors versus aluminum, which is typically what's used on mirrors that we use here on Earth for visible light. So that is the mirror. Now here's a little animation, or a little stop action video of how this telescope was actually finally folded up and assembled in order to be shipped to its launch site. And remember, all of this activity has to undo itself in reverse out in space after the launch. And there it is, ready to go. So now, what do we do now? We pack it into this giant container, which is very, very clean, and then we put it aboard a ship, send it through the Panama Canal, and eventually to French Guiana, where the European Space Agency has their launch capability. They built their launch site in French Guiana because it's nearer the equator. And because you know the Earth is spinning around, it turns out that the closer you are to the equator when you launch your rocket ship, the more boost you get just from the spin of the Earth that you don't have to actually provide with the rocket engines themselves. So by from French Guiana, in spite of all the trouble involved in being in a mosquito-infested jungle, they actually are able to launch larger payloads with smaller rockets, and it's quite successful down there. So off they go, and there in the top of the rocket is, of course, our James Webb Space Telescope. There's no spare, there's no plan B here. We're launched into space, and then eventually we give the telescope its final push out into space. And this is an actual video of the space telescope being released from the 3rd stage of the rocket. It's on its way out to that spot 1 million miles away from Earth with an exquisitely accurate push that delivered it perfectly to the spot it needed to be. And there it goes. Now, this place that's out there in space is called one of the Lagrange points. And a Lagrange point is a place where an object can stay in orbit without having to use a lot of fuel. So once we get to that spot, the telescope unfolds itself, expands something we call the sun shield, opens up the mirror, unlocks everything, and then there's a process of setting it up, aligning the mirror segments, and so on. Do we have any golfers in here? Anybody with golfers in their family? So think about this. This little spot in space is kind of like a golf cup, okay, but it's not 6 inches deep. Try to think about a 1,000,000-mile uphill putt with a cup that's maybe 1/4 of an inch deep at the top of the hill, and your job is to roll a golf ball up that hill with one stroke, 1,000,000 miles, slowing down all the way until it just makes it into that little 1/4 inch divot and doesn't roll out the other side. That's the kind of accuracy that was required here. Now, they did have fuel on board, and they could have used that fuel to fire little thrusters to slow them down or speed them up in case the push wasn't exactly perfect. But the push of those rockets was so perfect that almost none of the fuel that was loaded on board in order to use to slow down or speed up or hit that spot needed to be used. As a result, the telescope is going to get an extra 15 years of scientific operation, in addition to the 10 years that it was committed for, because it has that much more fuel on board that it can use to keep itself pointed in the right position. So the engineers who launched that rocket, that was their only job, and they did it so perfectly that this mission, we're going to get way more science out of this mission than we ever dreamed, because we've got plenty of fuel on board. So here we are, we're 1,000,000 miles out in space at this little place called the Lagrange point, and why do we have all this tennis court-sized stuff here? Well, that's because the telescope is sensitive to infrared light, which is a lot like heat. So if the sun were to warm up the telescope, the only thing it would be recording would be images of the heat that its own heat signature was generating, and that's not what we're looking for. So every part of the telescope out here and its cameras down here have to be cooled to the temperature of open space, roughly 350 to 400 degrees below zero. And they cool passively in that way. So the telescope is oriented in such a way that this side always faces the sun, and these 5 layers of mylar with coatings on them block all the heat from the sun and reflect it away. And the other side is the observing side, and that's where the telescope sits, always in the shadow of these 5 layers. They're the size of a giant tennis court. So try to imagine that trying to unfold itself out into space accurately. Oh, so that it worked fine. There's a little animation of what it means to be orbiting at a Lagrange point. So Earth is going around the sun, here's the sun in the middle, here's Earth, and here's the telescope, another 1,000,000 miles farther out than we are from the sun. And it's basically orbiting around that little golf cup that I talked about in a way that allows it to do that without having to use a lot of fuel. So that's where we do. And it always looks away from the sun. So as the Earth orbits the sun, the telescope gets to take a picture of the area of the sky that it's pointing at. 6 months later, when we're on the other side of the sun, the telescope gets to take pictures of the other part of the sky. But they can't turn around and take pictures over here, because then the sun would shine on the telescope and it would warm things up and it wouldn't work anymore. So we've been launching infrared telescopes into space for decades now. The WISE telescope was launched over 30 years ago, and you can see here's a picture of what an area of the space with stars in it looked like. This is a cloud of dust with stars being born. The Spitzer Space Telescope was launched after that, and it has much higher resolution. So you can see this is the same exact area of the sky. These are the same 4 stars here, and you can begin to see in this cloud of dust how some stars are beginning to be born out of this stellar nursery where stars get born. But take a look at what the James Webb Telescope was able to show us in that same exact area of the sky, with the ability to go deep into the infrared and see right through all this dust and gas, plus the fact that we have an 18-foot mirror instead of something smaller. You can see the detail that scientists can get out of the data that comes back from this telescope. It's quite amazing. What does it mean to see back in the cosmos? When we look out into space with a telescope, the farther you look out into space, the farther back you look in time. Every telescope is like a time machine, because it takes time for the light from these distant galaxies to get here. The closest galaxies, it takes 12 million years to get here. The ones farther away, 100 million, maybe a billion. And then the farther back you go in time, you start to get close to the time when the first galaxies formed 14.5 billion years ago, just after the Big Bang, when everything, as far as we know, began. So as we look out into space, farther and farther out into space, we're looking farther and farther back into time. And the earlier telescopes had a limit. They could only look out so far, basically to about 1 billion years after the Big Bang. But it turns out that most of the early galaxies had already formed by 1 billion years after the Big Bang. We couldn't look any farther because we didn't have the ability to look into the infrared. The James Webb Telescope gave us the ability to look an extra, 700 million years farther. And now we're able to see this part of the evolution of the universe, when the first stars were formed and the first galaxies were formed. And the scientists are giddy with the amount of information they're getting about this distant time and in our formation of the universe. We can't look any farther back than that, because before this, the stars hadn't actually formed yet, and we don't have light coming to us from the stars that haven't formed yet. So we're talking about seeing basically back to the beginning of the universe as we know it, that's filled with stars and galaxies. And this is what one of those pictures looks like. You might say, oh, beautiful stars, but in fact, every one of the 1,500 or so objects in this picture is a galaxy like our Milky Way. And each of them might contain 200 or 300 billion stars individually, like we do in our Milky Way. And some of those are really, really far away. In fact, this little dot right here, this little red dot right here, is the most distant galaxy that we've ever imaged. That galaxy was formed only 300 million years after the Big Bang, 1/3 of a billion years after the Big Bang. That's the earliest and oldest object that man has ever been able to image. And so studying these things tells scientists who, that's why they call them rocket scientists, right? They're a lot smarter than I am. They know what they're doing, and they're looking for data about this in order to decide between, which model of the universe's evolution is the right one and which one's wrong. So a couple of pictures from the Hubble and from James Webb. So here's another picture of a nebula, a cloud of dust and gas. What's going on here is this is a cloud of dust and gas where stars are being born. And up here off the screen is a very bright, hot star whose radiation is sort of sculpting away this material. And down in here we see some stars being born. But when we look at this same area, remember this little bump here, that's in the next picture. Here's the same image taken from the James Webb. There's that little bump right there. And now we can see deep into this cloud of dust, see all these stars being born, learn about the evolution of stars, how they're formed and how they evolve and how they live and how they die, and all that is tremendously important for the study of the evolution of the universe. These pictures are taken in black and white. I want to emphasize that even though that's a beautiful color picture, we don't see infrared light. If you look at an infrared source, you don't see anything. You might feel some heat on your face, but you won't see the image. Your eyes aren't sensitive, your retinas aren't sensitive. So the Hubble, the James Webb takes pictures in infrared, and they come out as black and white, like this. And then scientists, and some of them are young scientists, I'm so jealous, they get these pictures and then they go into artistic mode, where they say, okay, we have to shift these black and white pictures into the color spectrum that we can see in a way that is both scientifically accurate and artistically, aesthetically beautiful. So here's an example of what you might do with that kind of data. Right? We'll shift that into the red so that we can see the difference between old red stars that are ready to die and young blue stars that are young and hot and have just been born. So in this galaxy, there are lots of different things going on, and by adjusting the colors of the various wavelengths of light that get captured by the James Webb, the scientists are able to tell what's going on by just looking at it. So that's something else. Again, this is something called the Pillars of Creation. Did anybody come to our Dark Sky Festival? Good, few people did, and you saw that in our silent auction we had a print of this donated by Steve Gay, a local resident, and we sold that. But this is the Hubble telescope view of this, and this was my screensaver for years. It just blew me away. It's so beautiful. And then the James Webb version came out. And, you know, it was like, oh, I got a new shiny car. I don't want to drive that old Volkswagen anymore. That was my favorite car for a while, but not anymore. So, yeah, you can see totally different view here. We're looking deep, deep into this cloud of dust. We see thousands more stars that are being born and lots more detail. So scientists love this. I don't know what the next version of infrared telescope will show, but I can't imagine how it would be any more beautiful than this. It's really pretty. The telescope can also look at planets, and so the James Webb took a good look at the planet Jupiter and saw it in a way that we've never seen it before. You can see the great red spot is here. It's very hot and high in infrared energy, and so it looks white. We can see the details in Jupiter's atmosphere, all these cloud bands going by. Jupiter has some faint rings that are usually caused by moons that are ejecting dust into space as they go around. And it has auroras like northern and southern lights like we do on Earth as well. So the James Webb is really quite an amazing device. So just a quick recap. It orbits this Lagrange point 1 million miles from Earth, and in the next talk I'm going to talk about Lagrange points out by Jupiter. Every planet has 5 Lagrange points around it where you can orbit without using up a lot of fuel. Like I said, it's sensitive to near and mid-infrared wavelengths of light, which penetrates dust, lets us see deeper into space. That means we can see back into time, and that means that we can see things that are only 2% as old as the universe that we live in right now, which is quite a ways back in time. So that's that. So expect more wonderful discoveries for the next 25 years from the James Webb, thanks to the great job that the engineers did launching it. Okay, part 1. Now, did y'all catch that? Wasn't that cool? That was the segue into part 2. All right, I'll take a drink first. Now this part of the talk is very personal because this is something that Peggy and I did. So I've subtitled this, Peggy and Ted Go to Kansas, which is just what we did. So there's a mission called Lucy, and the Lucy mission is studying asteroids out in the asteroid belt. This is much farther away than the James Webb telescope. This is 400 million miles away. And most of the asteroids in the solar system orbit in this big gap between Mars and Jupiter. So they orbit around the sun kind of in this empty space. We've got 4 inner planets, Mercury, Venus, Earth, and Mars. Big empty gap, and then those are the rocky planets, and then starting with Jupiter, the gas giants, Jupiter, Saturn, Uranus, and Neptune, out to the outer parts of the solar system. But what are these things here, these 2 groups here? These turn out to be asteroids that have managed to find themselves a safe spot so that Jupiter's big old gravity won't suck them in and destroy them. Then they have found 2 of these things we call Trojan points in Jupiter's orbit. Earth has 5 Trojan points, Jupiter has 5 Trojan points. And we sent the James Webb telescope to Trojan point number 2, Lagrange point number 2, and these turn out to orbit in numbers 4 and 5 around Jupiter. So these are clusters of asteroids that have managed to find a safe place to orbit where Jupiter doesn't destroy their orbits, suck them in, or throw them out of the solar system completely, which happens a lot. So the Lucy mission was launched in 2021, and it's on its way now. It's going to have 2 main belt asteroids and 5 encounters with these asteroids that are called as Trojan asteroids at Group 4 and Group 5. The Lucy mission is named after the Lucy skeleton that was discovered in 1974 by Donald Johanson and Tom May in Africa, which was a skeleton that illuminated the historical development of humans over millions of years in Africa. And so they named this mission Lucy because it's going to illuminate the historical development of our solar system in the same way the Lucy skeleton tells us something about the history of mankind's development over millions of years. So it turns out that the Trojan asteroids that are in these two spots are not unique, they're not uniform. They're a diverse population. They're different sizes, they're different colors, they're different brightnesses, and so we're going to visit some of each of those. Some small ones, some big ones, some bright ones, some dim ones, some of red ones, and some brown ones, to make sure that we understand why they're all different and what that gives us in terms of understanding of the universe, of how our solar system formed. So this is the team that developed the mission, and they're in 2019 here, and their principal investigator, Hal Levison, this happy-looking guy sitting in the middle who looks like Santa Claus, is in fact the fellow who provided me with all this second set of slides. So thank you, Hal. And Hal was the organizer of the mission that Peggy and I went on as well. So what's going to happen when Lucy, how are we going to do this? How are we going to visit all these different asteroids? Well, we've launched Lucy out into space, and Lucy came back, and last year it passed by Earth and got what we call a gravitational slingshot. So it absorbed a little bit of Earth's momentum, and so it picked up hundreds and thousands of miles an hour of speed. In return, Earth slowed down a very tiny bit in our orbital speed, but we don't actually notice that because the mass of this spacecraft is slightly less than the mass of our planet. So off we go out into space at a little higher speed now, and we are now able to get a little farther away from the sun, and we are going to encounter an asteroid called Dinkinesh, or Dinky, in 2023 in November, and we're going to do a little rehearsal. We're going to pass by this. This is a main belt asteroid, but it's on the way out to the Trojan asteroids. Once we pass that, we continue to, now we fall back to Earth because, of course, the sun's gravity is constantly pulling the spacecraft back. We get another boost as we go past what we call Earth gravity assist number 2, and now we have enough energy to find ourselves going out farther from the sun. And we are going to go past an asteroid named after Donald Johanson, who discovered the Lucy skeleton in 1974. So we're going to test our equipment on an asteroid named after the guy who inspired the name of the mission. Once that happens, we don't have quite enough energy to make it all the way out to every part of the Trojans, but we are going to be able to swing by several Trojan asteroids. Euripides, which is a C-type, a brighter colored asteroid, and then after that, Polymele and something called Sean, which I'll talk a lot about later on. We'll also pass by another asteroid here called Lucas, and then finally an asteroid called Orus. And then we've lost our momentum, and so now we're going to swing back towards the sun. The sun's gravity is hard to avoid. It's pulling us back. We're not actually going to go close enough to that asteroid to study it. Another Earth gravity assist number 3, and that's going to be able to throw us out to the other set of Trojan asteroids that follow Jupiter in its orbit, the L5 group, and we're going to study one more asteroid over there, which is a binary pair of asteroids called Patroclus and Monoecius, and these two asteroids actually orbit each other, as you can see in this little animation on the bottom. So we've got quite a bunch of things. This is in 2033, and that'll be the typical end of the mission. Lucy will continue to orbit the sun for probably 2 million years. So there may be opportunities, if the equipment's still working, to study more and more asteroids, but that's the main mission, and then that will be the definition of success. So here's kind of what all those asteroids look like, relative size. But this is Polymele, and that little dot is something called Sean. It's named after Sean in the Wallace and Gromit cartoons. What is Sean? Well, some friends of mine went out to study the asteroid Polymele last year, and they studied it by finding a prediction that said that the asteroid was going to pass in front of a star at some point in its orbit. And if you were in the right place on Earth at the right time and pointing a telescope with a video camera at that star, you might see the star blink out. behind the asteroid. And that would tell scientists exactly where the asteroid was, which is useful if you'd like to take pictures of it when you go past it at 13,000 miles an hour. So the more information we have about the location of the asteroid, the better. And so what happened was the star blinked out as expected. You can see here these little red dots represent the asteroid blinking out. But then about 20 seconds later, a friend of mine from Scottsdale, Tony George, observed, he didn't see the main asteroid go in front of the star, but he saw the star blink out 20 seconds late, as did another fellow, Kirk Bender, who was a couple of miles away from Tony. That signified that this asteroid had its own little satellite or moon orbiting it. And so suddenly the Lucy mission had an extra target that nobody knew about when we launched the mission. And we don't really know where it is because we only have one little data point. At this point in time, it was there. But is it orbiting the asteroid? Is it orbiting the main asteroid this way, or that way? We have no idea, right? So we want to know more about it. So just so you know what it looks like when you videotape one of these events, here's a little recording of a star that's going to be occulted, or essentially eclipsed by an asteroid. You can't see the asteroid. It's too small and dark, but watch what happens to the star as the asteroid passes in front of it. So that only happens, you can only see that if you're in exactly the right place on Earth, at the right time, pointing at the right star, and you remember to push the button that says start recording. Don't ask why I know that. And so if we take software and we analyze how much light there is from that star in each frame of this video, we get a graph that looks like this. And the length of time the star disappears is a perfect measurement of the size of the asteroid. So we know how big the asteroid is, we know where it is, and we can do all that with cheap equipment and two people like us going out into the desert with a little tiny telescope and a recorder for way less than $1 billion that it takes to launch a mission to go up there and actually take pictures of it. But we do have a mission on our way, the Lucy mission. And these are some of the instruments on board, the instrument platform on Lucy. And Lucy has two giant, beautifully transparent solar panels to give it power from the sun. And that's why it doesn't have to have radioactive thermal isotope nuclear generator on board to generate electricity. It's using solar panels, and they have to be big because the sun is a lot dimmer out in the orbit of Jupiter than it is here in the orbit of Earth. Here's Lucy all wrapped up and getting ready to be placed into the fairing on top of the rocket. And then here we are in French Guiana, ready to launch about a year ago, and off we go into space. And we got a few well-wishers from a guy you might recognize.
I'm so excited. Lucy is going back in the sky time. Ronnie will love that. Anyway, if you meet anyone out there, Lucy, give the peace and love from me. And NASA, peace and love. It's just so great that we're heading out. I hope that when we reach Mars, now we may be going a little bit further. The water room, peace and love. Don't forget, my name is Ringo. Peace and love.
Yep, he actually did record that for the Lucy mission, people, which is pretty cool. Thanks, Ringo. So we launched the spacecraft. We're on our way out into space. Going by the moon, Lucy took a few really nice photographs of lunar craters, some of the best ever taken. They've got a fantastic telescope on board, designed by a friend of mine, Steve Kennard, and it's called LORRI, the Long Range Reconnaissance Imager. It's a copy of the one that took the pictures of Pluto that you might have all seen about 5 years ago when their spacecraft went past Pluto. There's a website called whereislucy.space, and if you go to that website, it'll tell you exactly where Lucy is right now over the next 12 years. So again, Peggy and I were invited to go along because it was predicted that Polymele and possibly Sean were going to pass in front of another star last February. So we had to go somewhere along the path where the shadow would pass across Earth of this asteroid. And this is the path of the shadow across the planet. You see, it crossed 3 continents, and it only took about 16 minutes for the shadow of this asteroid to pass across the whole planet. And so there were some observers in Spain and Portugal. Then the shadow went across the Atlantic Ocean, went through northern Canada, and it ended up crossing the United States right through the state of Kansas, ended up down here in about 16 minutes total, and then it was off the planet and out into space. And this happened at 8:30 p.m. on February the 4th. So we had to be somewhere in the shadow on February 4th at 8:30 p.m. So last November, we got this call to action. Find Sean. We want to know where it is, because when we go past Polymele, 10 years from now, we want to be able to take pictures of Polymele and its moon, its satellite, Sean, because that's another target, and we're going to be looking. We just don't want to miss it by just a small amount because we didn't know where it was. So the more information we have about it, the better. So what do? We send out 95 telescopes. So 150 people were flown to Denver. 2 of them were Peggy and myself. In February, temperature 6 degrees. We got to bring our Yosemite clothes, right? All the clothes, boots and hats and everything. Now the path of the shadow of the main asteroid, Polymele, is going to go between these 2 blue lines here. But where's the shadow of Sean going to go? It's tiny, and we have no idea where it is. So what do? We put out 95 telescopes about 2 miles apart, hoping that in the same way that a picket fence will catch a deer if it tries to stick his head through the slats, we'll catch the shadow of Sean. 1 or 2 of those telescopes we'll see the star disappear. In addition to the 4 or 5 in the middle that'll see it disappear behind the main body. And here we are. We're assigned track number 31. So somewhere down, we're on this red line here. We don't know where Sean will be. We have just as much chance of being the people to see this star disappear as anybody else. So what do? We go to Denver. We go into this giant warehouse, and 150 people start to get trained. Many of them have no idea what an occultation is. They don't know what an asteroid is. They have no idea what they're in for. But 4 days from now, they have to be out in the field with a telescope, all alone, 2 miles from the nearest partner, ready to point it at the right star at the right time. So it was a big learning curve. What do we have in this warehouse? 95 telescopes. Giant telescopes, 11, 10, 11, 12 inches, 16 inches in diameter. You can see them all here stacked up so neatly. All these have been purchased with grant money for exactly this reason. No matter how much money you spend on telescopes on Earth, it's 1,000,000 times cheaper than trying to send a mission out into space. So what do? Nighttime practice number 1. In Denver, we go out into the freezing cold. We go to dinner. When we come back, all of our telescopes have been carried out and placed in a little 6-foot square. That's your spot. Your job is to assemble a telescope, get it working, point it at a star, and try and find that star tonight, even though you're 4 days early. Just make sure you can find the star. So here we are. I mean, we're freezing. The telescopes fail, the batteries freeze, the computers stop working, everything that could go wrong possibly goes wrong, but it's okay, we have 3 more days to figure this all out. Right? Nighttime practice number 2, we're not together anymore. Now we put your telescope in the car, go find someplace all by yourselves and practice, practice, practice. So here we are practicing. We practiced a lot of things. Oh, did I put that in there? I'm sorry, honey. So we're done with that. We successfully find that star, even though we're 2 days early. Now get in the car, drive to Salina, Kansas. It's 6 hours. We had another couple of guys in the car. This is Rahul. He's a postdoc at Berkeley. He has no idea what an asteroid or an occultation is, but he thought this was so cool. He spent his whole Easter vacation at Berkeley working so he could take a week off to come and do this with us in Denver. And another young geology student in the Colorado School of Mines did the same thing. So they were a team with us, 4 people in the car. Got to the Kansas border, stopped for a break, and sure enough, there's Dorothy and everybody else. Practice night number 3, we're in Salina, Kansas. We still don't know which one of those lines we're going to be assigned, so practice, practice, practice. Again, set things up, make sure you can find the star. It's not, you don't have much time between sunset and 8:30, so you've got to be able to do this all quickly. Assemble the telescope, find the star, do an alignment, and so on. This is the part of the sky our little star was in. It's right under that little X. You can see Orion here on his side, Capella in Auriga and the Moon, Castor and Pollux, the Gemini twins. So we knew approximately where we were going. And this is what the computer screen looked like. We had this little laptop that we kept charged up all the time. When we got to our spot, who did we find? We found neighbors. We had neighbors. We wanted a place where we could get on our line, but be protected from the wind. And so we found some giant grain silos, and the farmer was kind enough to let us set up behind these giant grain silos, which we did right here. And that kept the wind, but it was still windy. So during the occultation time, we had a giant tarp, and the two of us just stood there with broomsticks and stood on the bottom of the tarp, held it up, and tried our best to make sure that the telescope didn't shake or move around at all. This is what the screen looked like. That's there's the star, right? You can hardly see it. There's the star that we were watching. We did not see the star disappear, so we were not the people to find Sean. The pictures in the middle, this is one of our teams in Kansas, and these are people in Spain who were doing exactly the same thing, but 16 minutes earlier. So the results, we had 5 positive events. 5 of the team in the middle did see the star disappear behind the main body. So now we know a little bit more about Polymele's shape and size and orbital speed and so on. We do have a tentative location of Sean. At least 1 and possibly 2 of the telescopes saw the star disappear. They were way up by Salina. They were 40 miles or so, 20 miles north of the main body shadow. So that's where Sean was at that time. So now we have 2 places where we know Sean was, 2 spots and 2 times, and we're starting to get a better idea of which way Sean orbits. I don't know all the details, but I know that there are certain orbits which are no longer possible because of these 2 positive identifications of where it was. So that helps in the future. More data is required, so our bags are still packed. And if they call us again, we will definitely head out and do this again if time permits. Finally, I want to remind folks about this fantastic NOVA program. I know some of you have seen this already. We talked about it earlier, called the Star Chasers of Senegal. Our team, this team that invited us a year ago, went to Senegal for another one of these occultations and used that opportunity to encourage local astronomers in Senegal to become active in amateur astronomy like this. And the NOVA teams were there filming this, and they put together a fantastic 1-hour show on NOVA. So if you've got that recorded, or you can go to the PBS website, that's really quite a fantastic show. And you'll see this is one of the smaller telescopes. In fact, this is the exact telescope that our partners, Rahul and his friend, used. They had the small 8-inch telescope, and we had the larger 16-inch telescope. So I recommend this highly. It's a fantastic program, Star Chasers of Senegal on PBS.